Hi, and welcome to the first of our videos on forces. We're just going to look quickly and briefly at how we describe forces using vectors and the type of language that we use to describe how forces are acting on objects. So let's get started. In this video, we're going to talk about the three ways that we can see forces acting on an object. So how we talk about knowing that a force is acting. We're going to talk about vectors and how we use vectors to illustrate forces acting on an object, how we label those forces, and then how we're going to list the Welcome to our first video on forces. In this one, we're just going to review some of the content that you will have studied in previous topics on forces, look at how we describe them, and move forward from there. So let's look at our learning intentions. So in this video, we want to be able to describe the three ways that forces act on an object and how they can be observed. Use vectors to illustrate the forces acting on an object so we can describe them accurately. Then be able to label the key forces on an object using those vectors, as well as being able to describe the way resistive forces work and how we can show those as well. So let's get started. Forces simply, and you will have probably covered this in previous year levels, allow us to describe push-pull actions on an object. Okay, so there are always forces acting on all objects all the time. And these, we should remember, can be contact forces. So this is where two objects come touching when they're contact forces. So you see these forces when you're sitting on a chair, okay, and you don't fall straight through the chair. You can feel that pressure of the chair pushing back on you and you pushing down on a chair. They have a contact force. There are also non-contact forces, which we can observe when we allow something to fall, and this is the force due to gravity. So generally we describe forces as being a push, pull, or a twist that allows us to move an object or start it moving. Okay, we can observe these by seeing an object changing shape. Okay, this will allow us to know that a force has been acted on it. So if you apply pressure to a sponge, we know that it will change shape. That is one way that we can tell a force is acting on something. We can see the motion of the object change as well. And this is what we're going to talk about largely in this unit, is how forces allow us to change motion. This means it can speed up, slow down, something can start moving or stop moving. And these are ways that we know that an object has a force acting on it. When it comes to showing forces, we rely on a mathematical quantity known as a vector. So a vector is essentially an arrow that has a starting position, which would be the tail. It moves in the direction of movement, and then we have the head or the end of the vector. From the tip of the tail to the tip of the head is the magnitude or the amount that this arrow is representing. And of course, because it's an arrow, it has a direction. We use vectors to illustrate forces that are acting on an object because they give us both the size of the force and the direction of it. So we can see here with this vector, we have it moving in this direction to the top right, which gives us vector A. If we were to reverse that vector, we would have negative A. So the negative sign in terms of vectors allows us to show direction. So the negative in this case says that this vector is in the opposite direction to A, but the same size. Okay, so we can use vectors to display how forces are acting on objects. In this diagram here, we have a number of vectors and we have a size, a magnitude of the force that is being applied to it. The force is given the unit of newtons, and in this case we would have a 9 Newton force acting to the right and a 3 Newton force acting to the left. The beauty of vectors is that if we take one vector and then we add it by placing the other vector at the tip of that one and then running it in the direction that it goes, in this case 3 newtons, this one 9 newtons, we can see that this would end its journey at what would be an equivalent of 6 newtons to the right, and we would refer to this as the net force. So the net force of acting on an object is equal to the sum of all the forces. Okay, remembering that if they are in opposing directions, that would get an opposing sign. So in the case of C, again, we have a 9 Newton force to the right and a 3 Newton force to the left, and this would still have an overall net force of 6 newtons to the right. Okay, on E, we can see that we have no force pointing to the left, so the net force is going to be the same as the driving force, and in this case it is 6 newtons. B, we have an overall net force of 9 newtons to the right. D, it is 3 newtons to the right. And we can see with F, if we have 6 newtons to the right and 3 newtons to the left, we have 6 newtons minus 3 newtons because it's in the opposite direction, which means that we will have a 3 newtons to the right as our overall net force. Okay, so this is the way that we can show vectors acting on an object as force vectors. So we can see what way the force is acting. If we have a force, an overall net force in a particular direction, like this one with 9 newtons to the right, it means that this would have a thrust force that would be causing it to accelerate in the direction of the larger arrow. Okay, so remembering that if we have a force being applied to an object, a constant force being applied to the object, and nothing resisting that force, then we will be seeing an acceleration. We'll be seeing a change in its motion. So when things aren't moving, we know that the forces are balanced because we don't have a vector pushing us in one particular direction. We can see this when things are resting on a table. We will have a force due to gravity, so we can label our force due to gravity. And you may have heard this being called weight in the past, but we are going to use the term Fg, which is the force due to gravity. Every force, when we have a contact force, the box is pushing down on the table with the force equal to its mass times the acceleration, which is our force due to gravity. And then we have the box, the table is pushing back on the box. The force that acts perpendicular to the contact force here, or perpendicular to the force due to gravity when they are in contact, is the force or normal force. We give this Fn as the symbol. So every time something is in contact with each other, we will have the force due to gravity, which acts from its center of mass, and then the force that pushes back up against that, the force normal. And we know that normal force is there because if it wasn't, then we would pass through things. If we pushed down onto the ground and the ground wasn't pushing back on us with equal force, then we would sink into it. Okay, so you can see this if you walk across a spongy mattress. As you push down on it, it gives way and it changes shape because it has that unbalanced force acting on it. So when we talk about drawing forces acting on an object, we can see here on every person, we're going to have Fg, which is pushing down, pushing us down towards the center of the earth, or pulling. And then the normal force, the force normal, okay? In this case, this would be our driving force or thrust that is being given to us by the foot pushing down on the ground and us giving traction. So that's pushing the runner forward. And then we're going to have friction or air resistance that is the friction force pushing back against that movement. Okay, when the forces are balanced, when all forces are balanced, then motion is constant. Okay, that means that there's no change in the speed of the object, okay, if the forces are balanced. So if the speed of the object is 0 meters per second because it's stationary, then the forces are balanced. If the speed of the object is 5 meters per second and it is a constant speed, then our forces are also balanced, okay, because there's nothing causing it to accelerate in the forward or negative direction, i.e. it's not speeding up or slowing down. One of the other things that we need to be able to describe when we talk about describing forces is the friction force. And these are resistive forces that always oppose the direction of movement. Okay, if you think about if you're riding your bike and you coast down along a road, generally, you will coast for a while, but you will eventually slow down and come to a stop if you don't start pedaling again. And this is because the force of friction between the tires and the road, which allows you to have traction to speed up as you apply force through the pedals, will also slow you down over time if you don't keep applying the force. So if we draw this as a simple object, as we push forward with our feet on the pedals, we're going to have our driving force, okay, which is our driving force, FD. We know that we're on a surface and we're not sinking through it, so we've got our normal force and our gravitational force. But then if we're speeding up, okay, so we're pedaling and we're providing thrust, then the driving force is going to be greater than the friction force, okay, so we will speed up. If we're traveling at a constant speed, then the driving force and the friction force are going to be equal, okay? So friction is always in opposition to the movement. And there are a number of different things that can influence friction, which is how smooth the two surfaces are, because it is always a contact force. So the less contact between the two surfaces, or the smoother the contact, the less friction that we're going to have. Okay, so if things are rough, we will get more friction, and also the shape. Okay, so we talk about aerodynamic shapes where air can pass over, or in the case if we look at the curling stone, we can see that it is curved at the bottom, so it has minimal contact with the ice, okay, so that it doesn't have many contact points in order to reduce the friction. Okay, if we think about the way that cyclists' helmets are, they have an aerodynamic shape that allows them to have the air pass smoothly over them and not produce a lot of drag. So things like surface area, if you can think, if we have air pushing against a large flat surface, that will slow us down, versus if we can decrease the profile that is being presented towards the air. So with friction, it's all about decreasing the overall surface area and making sure that we have less contact, so less contact forces, but it is always in opposition to the movement. Okay, so that's a brief rundown to review us on forces. Next, we'll look at Newton's laws.